Okay. So last time we looked at chapter 1, which is related to how to measure the performance of the computer systems, and also we look at the anatomy of the computer systems. So the most important thing is the process part and the memory part, right? So from today, we will learn about the process part, okay? We'll learn about the chapter 2, which is very important. So if you are missing this chapter 2, then it's very hard to follow this class, okay? So we will look at the instruction, okay? So machine instruction. Okay, so we learn about the instruction set first, okay? So each computer system has its own instruction set, okay? So different computers have a different instruction set. Even though commonly many instruction sets are common, okay? So anyway, we will learn about the specific instruction set for the specific computer systems. Historically, early computers had very simple instruction set, which means that number of instruction is small and the format of instruction is very simple. Okay, so it's simplified. And then later, it was becoming very complicated, and then it's coming back to the very simple. Okay, so let me write down the instruction. So when the computer system is invented or process is invented, the first instruction set is very simple. Okay, and then 1970, middle of 1970, Intel, you know was the Intel company, right? Intel company was introducing the microprocessor or processor. So they are creating Intel processor. And then later, the Intel is upgrading their Intel processor by adding more instructions. So for instance, if we need some specific instruction set, then Intel is adding that instruction into the processor. So whenever new process is coming out, new instructions are supported by Intel. So it's getting complicated. Nowadays, you are using the i5 or i7, right? These processors you are using. Do you guess how many instructions are supported by Intel processor? Number of instructions? So currently you don't know what is instruction, right? So we'll learn about that. Intel processor case, it is almost 1,000 instructions. Almost 1,000 instructions. So this kind of architecture is called complex instruction set computer. So we are calling it as CISC machine, okay? So Intel was thinking that if we can provide a very complex instruction, then using that instruction, we can do a lot of things, okay? So which means that if we are providing very complex instruction, then we can improve the performance of processor. That's the plus of Intel, okay? So, but it is actually changed. Early 1980, the writer of our textbook, who are Hennes and Patterson, they are finding that actually, even though there are many instructions, but normally small number of instructions are commonly used. Okay, and also if we are making a lot of instruction, then the processor is getting difficult to be implemented. So they are reducing the number of instructions, which is called reduced instruction set computer, which is abbreviated as RISC machine. Okay. So in the RISC machine case, the number of instructions is much smaller than that, the CISC machine. So here in this case, it is like 250 instructions only. Okay. So we will learn about the MIPS computer system, MIPS processor, and which is a RISC machine. And also, maybe you heard about the ARM processor, right? So your smartphone or Apple is using the ARM processor, right? So like M1, a smartphone. These are using this ARM processor. ARM processor is a reduced instruction set computer, which means that the number of instructions is much smaller than that Intel processor. So at least if we are comparing the CISC and RISC, then so CISC case, there are so many instructions, and RISC case number of instructions are small, which means that after we are getting one instruction, so which is provided to the processor, then processor has to analyze what this instruction is. Okay, we need analysis. So CISC case, this analysis takes a lot of time compared with RISC machine. And also for this analysis, a large area of processor is used for this analysis part. So this much is for the instruction decode. In CISC machine. In RISC machine, the instruction decode is much simpler because the format of instruction is very regular and also is very simple. So RISC case, instruction decode is very small. Instruction decode area is very small. So that if we are comparing RISC and CISC machine, then performance is, the RISC is providing the higher performance than the CISC machine. So that's the reason why maybe you're using the Apple M1 computer, right? Apple M1, and also Apple has like Intel, the previous one, last year they are using the Intel processor. If we are comparing these two processors, then M1 is consuming less power, and also the performance is higher than Intel processor. The main reason is the instruction sets are different. So M1 case, it is using the ARM instruction set, which is a RISC machine. Intel case is a CISC machine, so that the analysis part of the instruction is very complicated. Okay. So anyway, in this class, we will learn about this MIPS processor instruction set. Okay, so it's a much regular, and the instruction set is similar to the ARM processors. Okay, so we will learn about the MIPS instruction set. So we will learn about the MIPS instruction set. So all example will be MIPS, and MIPS was commercialized, but these days, the commercial one is actually is not exactly the same to the MIPS instruction set, but RISC-V is open source. It's very similar to the MIPS. Okay. So after your understanding of the MIPS instruction set, then you can easily understand the other processor architectures. Okay. So MIPS is actually a reference of many other instruction set computer systems. Okay, so then let's look at the instruction. So before that, let's look at the C code. C code, that's the high level language. So C code, we are writing the code, for instance, A equal B plus C plus D. Okay, so we are writing this kind of code. Then what we have to do is we have to translate. Translate to the machine code, machine instruction, or MIPS instruction. But this machine instruction case, it is very simple. Simple instruction. If the instruction is very complicated, then analysis is more difficult. So the instruction format is very simple. Instead of many addition things, simply it has only one addition. So in C code, normally we can write this code, A equal, like, okay, E equal B plus C, and then A equal E plus D, right? So we can write this kind of a simple code, right? So we can make this simplified. Then for each line, we can write down the mapped instruction. So here, this is addition, right? So for this addition, there is corresponding instruction in the MIPS, which is add instruction. And destination is E, and source is B and C. Okay, so in the C code, we are writing the left one. So we are writing this kind of approach, E equal B plus C. But in the assembly code or machine code, this is called assembly code, we will use the following format. So here, the first one is operation, OP code, operation. And the last one, these are operand. Okay, so in order to understand the assembly code or the machine code or instruction set, we have to know about what kind of operations are available, and for each operation, what operands are required. So if we know that this operation and operand, then we can understand all the instruction set. Okay. So in C code, there is a addition operation, right? And subtraction, multiplication, and division, modular, right? So there are so many things. So this is a C keyword. Then similarly in the MIPS instruction, it's very similar. For this addition, the instruction set is add. Minus, which is called subtraction. Multiplication, there is mul instruction. And this is a division and division instruction. And percent is modular. Modular is actually part of the division, actually. Okay. And also for each operation, the operand number of operands are 3. Okay. So 3 operations always. So A is B plus C. That meaning is B is E plus F. So first one is generally is the destination. Okay. So this kind of approach we will use. So the instruction set is not going to be hard. Okay. So for each operand operation, we will map to the corresponding instruction. Okay. So in the MIPS case, it's very regular. So for almost every operation, the number of operands are at most is more less than, at most is 3. Okay. So plus minus case, there are 2 source and 1 destination always. Okay, so this is a arithmetic operation, two source and one destination. So the first one is operation, and the first name is destination, and this is first source, and this is second source. Okay, so that's the format of each instruction. So in MIPS, every arithmetic operations have this kind of format. Okay, so some operation, and first one is destination, and two source. Okay. So the reason is, if we are making the instruction format is regular, so if we are giving the regularity, then making the hardware is much simpler. Okay, so later we will also design the hardware. So if instruction set is very depending on the operation, then it's very hard to decode. Okay, so format is very regular, then making the hardware is much simpler. Okay, so now let's understand how the processor is learning or executing the instruction. Okay, so let's try to understand. So there is a processor. And there is a memory. Okay, so execution of application is interaction between processor and memory. So it's interacting. So every instructions are stored in the memory. Okay, so memory has instruction. Add instruction. So definitely there is something, right? Destination, source one, source two. And another one, subtraction. And something, destination first source minus second source. Okay, so these instructions are stored in the memory. Okay, so then processor, what process is doing is, processor is sending address to read some content from the memory. Then, so for instance, each memory space, there is a number, right? So this number is called address. This is called address. So its index is actually address. So processor is sending address, then it is returning the content. So here, this case, the returned value will be, if it is 0, then first one, add something, something, something is returned. So processor is receiving this instruction. Okay. Then what process has to do is, process first analyze what this instruction is, right? First is looking at the first thing, which is add. Okay, is add. Then what's next? Next part is, if this is add, then we have to read the data, source data and second source, and then we do the addition, and that the result should be stored into that place, right? So for instance, let's say this is ABC. 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 So add instruction should be read data from B and C, and then to the addition, and then results should be stored into the A. But here we have the problem. Where is B and where is C and where is A? Right? So A, B, C are variable, right? This is variable. In C code. So in general, variable should be located in the memory. Okay, so which means that to read data for B is located someplace here, and C is here, A is here. So then the B value should be read from the memory, and C is also read from the memory, and then to the addition, and then store the result into the A location. But this case, we have to access memory frequently, right? But reading data from the memory or writing to the data to the memory, it takes a lot of time. So to save or to reduce the interacting with the memory, there is a small and very fast memory inside the processor. So inside the processor, there is a very small memory dedicated for each instruction, which is called register. So register is very fast, and the size of register is very limited. Okay, MIPS case, number of register is 32. Okay, so from 0, 1, 2, and 31. So there are 32 registers, and each register is 4 byte. 4 byte means is 32 bit. Okay, so there are 32 registers, and each register size is 32 bit. Okay, so instead of reading data from memory, we are specifying the location of register. So we are specifying index of register. Okay. So what index is, for instance, you are reading data from the first register. Okay, so it has some value, right? 5. From second register, 2, which is like a 7. And then store into the register number 3. So we can specify this kind of thing. So add 3, 1, 2, that means we are reading data from register 1 and register 2, and then to the addition, and then result into the store into the register 3. To specify the register index, we are using some special symbol in the MIPS, which is $sign. So $1, $2, $3. That means this $1, $1 is register 1, $2 is register 2, $3 is register 3. Okay, that's the format. So here in this case, $1's value is 5, $2 has 7, and after addition it will be 12. So after learning that instruction, then register 3 has 12 value. So after learning that instruction, add instruction, then register 3 value will be changed to the 12. Okay. And then processor is generating the new address. So next address. Then new instruction, which is subtraction. So for instance, $1, $2, maybe $2. So anything is okay. So then new instruction is fetched. And then processor is analyzing the instruction, which is subtraction. Then it is reading register 2 value, and register 2 value, which is 7, 7. So 7 minus 7 is 0. So 0 is stored into the register 1. So after learning subtraction, then register 1 value will be changed to the 0. Okay, so this is repeated. So every cycle, new instruction is fetched, and then that is executed, and then the register value is changed. And then next cycle, next class cycle, next following instruction is fetched, and then that is executed. So every cycle, on instruction is executed. Okay, so that's how the process is running application. Okay, so maybe you can understand, but maybe it's better to have use some real example. So first, we are learning about the one instruction, add instruction. Okay, so add instruction. So register 1, register 2, or something, register 3. That means register 1 value is register 2 plus register 3 value. So that instruction. Okay. We will learn about another instruction. So for instance, like this, A equal B plus 3. So this case, this is destination, B is source register, and 3 is constant value, right? Constant. So to specify the constant, there is another instruction, which is called add I. Okay, so this is add I means immediate. Okay, so add I is representing the last one is constant value. So here, $1, $2, and 3, for instance, like this. That means $1 is $2 plus 3. So this is constant 3. Okay. So for instance, $1 is 2. $2 is 5. $3 is 4. So if you're learning add $1, $2, $3. So after learning, then what's $1's value? It will be, you can write down into the chat window. Yeah, it will be 9. And add I, $1, $2, 3. Then what's the $1 value? It is 8. Okay. So then let's try to use the simulator, MIPS simulator. So we'll use this MIPS simulator. Let's go to the in slide 36. Then there is some website, right? So can you go to that website, first one? So can you click and then go to that place? Then you can see that so I am giving the website into the chat window. So if you can see the chat, you can see. Okay. Then you can see this kind of window, right? So can everybody look at? Then here, so there is an assembly source, right? Assembly source. So you can write down the code. So for instance, add I. 1, 0, 5. So then what will be the $1's value? After learning, $1 will be 5, right? And I, $2, 0, 7. Then add 3, comma 1. After you're writing the code and then do the assemble and load button, then you can see that it's changed, right? So $1 is here. I mean, the CPU status is representing the register value. So here $1 is actually R1, okay? And R2, R3, these values are 0. So everything is 0. It's hexadecimal representation. But if you can change into the decimal representation, so decimal, hexadecimal. So let's do the step. So first, the first instruction is waiting for execution step. Then the first register value will be 5, right? So $1 value changed to 5. And then next step, second one is 7. Last one, step, then 5 plus 7 is 12. In hexadecimal is C, where decimal is 12. Okay. So can you write this code on your simulator? And also, can you share your screen? I think everybody can share, right? So can you share your screen, everybody? Can you do it? Can you share your screen or not? Let me think. Okay, can you do it now? Okay, maybe it's not going to be possible to share the all everyone. Okay. So anyway, so can you try to do that one? It's working, right? So is there anyone who has the problem to learning the simulator? So if you have a problem, can you let me know that through the chat window? So everybody has no problem, right? Is there anyone who has difficulty to use? Okay. Okay, so you can stop the sharing. Stop the sharing. Okay, so I think everybody has the problem. So if you have any question during the simulator using, please let me know, then I will help you. Okay, then let's look at some example. Okay, so let's look at this code. F equals G plus H minus I plus J, right? So this is complicated because there are 3 operations to addition and 1 subtraction. So here in this case, what we have to do is we have to divide into the 3 instructions. Okay, so first we have to do first addition, and second addition, and last we have to subtraction. So here let's assume that G is 3, H equal 5, I equal 2, J equal 1, like this. So what we have to do? To assign this value, what do we have to do first? Which instruction do we have to use? So for each variable, we have to assign the register number first. Okay, and then register 1, we have to assign the constant 3. So to do that, we have to use add R instruction. $0 will be 0. $2 will be 5. $3 will be 2. 4 will be 1. And then first one, G plus H, which means $1 and $2 should be add. So add $1, $2, and then the result should be stored into some register. So $5 is non-use, so $5. And then second one, I plus J. I is 3, J is 4. And then store into the 6. And then add, not add, subtraction from $5 to the $6, and results should be stored into the sum register. Okay. So can you write down this code in the simulator, and can you check what's the $7's value? So if you are completing, please write down your answer in the chat window. Oh, that would be incorrect. 0. So if we are completing, please write down your answer in the chat. Okay. Okay, so then let's look at some example. Um, so there are two exercises. So the last one we didn't learn about them yet. So can you do the exercise 1 and exercise 2 now? Okay. What is this meaning? The I $1 plus plus, that is meaning yes, $1 is $1 plus 1. Okay. So can you do the exercise 1 and exercise 2 now? And if you are finishing, then please let me know. So you have to write down the answer. Okay, so many students are completed, right? Okay, so maybe you are really familiar with how to use the simulator. Okay, so we learn about the very basic instruction, add instruction, and add I instruction. Okay, so we will learn about the more instructions. So the first one will be memory operation, arithmetic operation. So we know the arithmetic operation like add instruction, subtraction. So now let's look at the memory operation. Okay, so main memory, we know about that. For the arithmetic operation case, like add instruction, subtraction, or others, everything is requiring the registers. So index should be a register. So there is no way to access the memory operand. For memory operand, memory access, there will be spatial instruction. So for memory access, so we learn about the two instruction. One is load instruction, and the other is store instruction. Okay, so there is a processor and memory. The load instruction is load reading data from the main memory. Store instruction is changing the data in the memory. Okay. So load and store case, what we have to give is address. We have to give the address first. Okay. So which means that we have to specify the address first, right? We have to specify the address. So for specifying the address, we are specifying register number here. So register 1, for instance, like this. Okay, so register 1 has the value. Register 1 has like a 1000. Then meaning is address will be 1000. So if we are using this instruction, load $1, then 1000 address, there is 1000 address. There will be some data here, 13 for instance. Then the 13 is returned to the processor. So processor is receiving that 13 and then store into the register. So for instance, this is $2. Then $2 will be changed to 13 after that instruction. Okay. So that's the page format. Load case, we need the first register is kind of destination register. So the first register will be changed. The second register will be the address one. But when we are learning the add instruction or add I instruction or subtraction instruction, the number of operands is 3, right? Load instruction case, only 2 are used, 2 registers only, right? So only 2 registers. So maybe there is another thing is left. So we are using some immediate value, like 4. So that meaning is this is meaning is address is $1's value plus 4. That's the address. Okay. So we can give some constant value in the address. So which means that here, if we are learning that instruction, then address will be, it's not 1000, address will be 1004. So that 1004, which value will be maybe 21 will be returned. Okay. So this kind of format is used. Load case, destination, and some address, and here constant value offset. These are format. So load $3 something 0 or 2 4 $. This kind of format is used. Then $3 value will be updated by $1 plus 0 and from memory. So this notation we will use. So this bracket means the data is read from the memory. Okay, so memory data is read and then change into the or store into the register number 3. Okay, store instruction. The format is the same. $2, 4, $1, like this. $3, 0, $1. So format is same. The direction is opposite. $3's value is stored into that address. So for instance, if we are running this instruction and $3 value, let's assume that $3 value is 7. Then store instruction is given to the memory. Store address is 1004, data is 7. Is going to the memory. Then memory is receiving 2 information, address and data, and memory is updating the content from the instruction, the command. Okay, so then let's look at some exercise. Well, let's do the exercise. So what we are doing is, let's try add I $1, $0. Let's say we are saying 1000. Okay. Then add I $2, 7. Okay. And then we do the store. Even though we learn about this store instruction, but we will store a word. Okay, so 4 byte. So we will learn about the SW, which is actually SW means store word. A word, one word. One word is actually 4 byte. This is command, I think. Charlie will be the command. Store $2 value into 1000. So let's look at what is happening. Okay. So before we are learning that instruction, let's look at the memory. Okay. So let's look at X1000 location. So if we are changing that part, then we can look at the memory location also. So 1000 location, everything is 0, right? Then we are learning. Step. So first one, 3E8, that's the location. 1000 is a decimal value and 3E8 is hexadecimal. So we have to look at that location. X 3E8 location. So nothing, right? Everything is 0. And step. So register value 2 is 7. And then store $0, $1, that is 3E8 and is storing 0, 0, 0, 0, 0, 0, 0, 7 value. So step. Okay, 0, 0, 0, 0, 0, 0, 0, 7. So this is 4 byte. This 4 byte is stored. Okay, so this is 1 byte, another byte, another byte, another. So 4 byte is 1 word. So this value will be stored here. Okay, so can you write down this code in your simulator? And if you have a question, please let me know. And also, if you are completing, then please let me know also in the chat window. Okay, someone is asking me that why the 07 is located in the fourth place, right? Not from the 0. Actually, that instruction, store instruction, is not storing the 07. It is storing the whole value. 00000007 is stored. Okay, so this 32-bit 4 bytes are stored into this memory. Okay, store word instruction is storing the one word into the main memory. Someone is another asking me that this 0, what that means 0, right? So this is address offset, which means that when we are generating the address, $1's value will be 1000, which is 3E8, okay? Plus 0, that is actually address. That is. So let me show you another example. If this is 4, or this is 8, then what is happening? Okay, so let's look at what is happening. Step, step. Okay, so here in this case, $1's value will be 3E8. So this is 3E8, 3E9, 3E8, EA, 3EB, and here another 4 byte, and this is another 4 byte. 4 byte. So if you're learning that instruction, then this last 4 byte will be changed. So when we are generating the address is actually A plus $1's value. So this is constant value. Address is $1 plus 8 in this case. So this 8 is called offset, address offset. Then also you can do the load instruction, load word. 3, like 0. Step, step, step. So last one is a learning, then $1. So this is read into the register number 3. So register is changed by load instruction. Okay. So maybe it's the first time. This is the first concept to you for this address thing. So maybe at the first time it will be a little bit hard to follow. But maybe after you're familiar with this approach, then memory is just large array, just array. So for this large array, we have to give the index, right? Specific index. That index is called address. So for index, we are using the two parts. One is register value and also constant value. So adding this register value and constant, that is generating the index. That index is accessed. So everybody done for this one? No question? Okay, so we will continue about this instruction set architecture for the load store instruction and the other arithmetic and logical operation in the next time. Any question? Okay, so have a good time. Bye.